Part 1. The Old Genius and the Young Rebels. Imagine you spent decades building modern physics, that at 26, you rewrote the laws of the universe, explained why time slows down at high speeds, why gravity curves space, why light and matter are the same thing. The world calls you a genius. Now imagine that at 56, you try to warn your colleagues about a serious flaw in the most modern theory of physics, and they ignore you. Worse, they whisper that you've gotten old, that the brilliance is gone, that you can't keep up with the science you yourself helped create. That man was Albert Einstein. The error he pointed out? No one took it seriously for decades. But Einstein was right. And the story of how the world finally discovered this is one of the most fascinating and disturbing in all of science. At Part 2, the sacred principle. To understand the problem, we start with an idea Einstein considered sacred. Nothing can move faster than light. Why? It's not arbitrary. It's a profound consequence of how the universe works. Newton believed gravity acted instantaneously across any distance. If the sun disappeared right now, Earth would feel it immediately and fly off in a straight line into space. But Newton himself found this absurd. A force that acts without contact, without delay, through the vacuum of space? It seemed like magic, not physics. In 1905, Einstein showed Newton was right to be bothered. Instantaneous action at a distance doesn't just seem weird. It creates real paradoxes. Here's the most devastating one. Two observers moving at different speeds disagree about when events happen. For you, two things occur at exactly the same time. For someone speeding past at high velocity, one happened before the other. Both points of view are equally valid. Apply this to Newton's instantaneous gravity. You see the sun disappear and Earth fly off at the same instant, exactly as Newton predicted. But the observer in motion sees something impossible. They see Earth fly off first, even while the sun is still there and should still be pulling Earth inward. To them, it looks like cause and effect are reversed. The effect comes before the cause. This isn't just strange. It's a logical impossibility, a contradiction that cannot exist in a consistent universe. The only solution: reject the assumption that any influence can be instantaneous. And that's exactly what Einstein did. It took him 10 years to fix this problem, and in the process, he completely overhauled our understanding of gravity. Einstein delivered general relativity, a new physics of gravity where effects propagate locally from point to point, never exceeding the speed of light. If the sun vanished right now, we wouldn't feel it for about 8 minutes. Not because information would be traveling to us, but because the fabric of space-time disturbed at that point takes that time to ripple outward until it reaches us. Physics was saved. It was local, it was causal, it was elegant. And then came quantum mechanics. Part 3, the Solvay Conference, Brussels. The greatest physicists on the planet gathered to discuss the new quantum theory, a mathematical structure that predicted the subatomic world with absurd precision, but which no one could properly explain. As one of the most famous photos in science was taken there. About 29 scientists looking at the camera. Nearly 2/3 of them would win the Nobel Prize. Einstein was among them, and he wasn't happy. He took the stage with a thought experiment. Simple, elegant, deadly. Imagine firing a single electron through a slit toward a circular detection screen. Quantum mechanics says this electron travels as a wave function that spreads through space, describing not where the electron is, but where it could be, with different probabilities at different points. When the electron is detected at a specific point, say here, the wave collapses. The probability of finding it anywhere else instantly drops to 0. But Einstein asked the question that deeply bothered him. Why doesn't the electron also appear at another point a moment later? After all, the wave function covered both places. The answer from quantum mechanics is that when the electron was detected at the first point, its wave function collapsed to 0 everywhere else instantaneously. How does the wave function know it must collapse to zero everywhere else at the same time, no matter how distant? It covered potentially astronomical regions of space. Quantum mechanics answer. When we detect the electron at one point, the wave function collapses instantaneously throughout the entire universe. The collapse is immediate. Information about the measurement must spread faster than light. Einstein turned to the audience and said, "This violates relativity. This requires influences that travel faster than light. This is, in his words, such a peculiar mechanism of action at a distance that implies a contradiction with the postulate of relativity." The silence was awkward. Niels Bohr, the great architect of the dominant quantum interpretation, the man whose institute in Copenhagen had become the world center of the new physics, said he didn't understand the argument. Literally, the most influential physicist in the world publicly confessed he didn't know what Einstein meant. One audience member recalled, "I feel myself in a very difficult position because I don't understand precisely what is the point which Einstein wants to make. No doubt it is my fault." That man was Niels Bohr himself. But this didn't prevent the story from being told decades later as an overwhelming victory for Bohr over Einstein. So part 4. The problem of interpretations. Why did modern physics adopt Bohr's view so quickly, even without fully understanding it? Part of the answer lies in the philosophy he formulated, the Copenhagen interpretation. For Bohr, quantum mechanics didn't need to say what the electron does when no one observes it. Physics doesn't describe reality. It predicts measurement results. The wave function describes everything you can know. Asking beyond that makes no sense. Einstein couldn't accept this. In letters to Schrödinger, he called the Copenhagen interpretation a tranquilizing philosophy, a way to make difficult questions disappear. For Einstein, physics had to describe reality. If the theory couldn't do this without invoking instantaneous actions, then it was incomplete. Yes, there were hidden variables, details about the electron's real state that quantum mechanics didn't know, and which, if known, would eliminate non-locality. But convincing Bohr was impossible. So, in 1935, Einstein changed strategy. Part 5. The paper that changed everything with two younger collaborators, Boris Podolsky and Nathan Rosen. Einstein published in 1935 a paper that would forever be known by the author's initials, EPR. The argument was surgical and devastating. Imagine a high-energy photon that decays producing two new particles, an electron and a positron. To conserve total electric charge, one must be negative and the other positive. But there's another property that must also be conserved: spin. If the original photon had zero spin, then the sum of the spins of the two children must also be zero. Here's the crucial detail that would change everything. Quantum mechanics says neither has defined spin before being measured. The electron isn't spin up or spin down before measurement. It's doing both at the same time, in superposition. The same goes for the positron. The only restriction is that the two must be opposite. When one is measured, the other will have the opposite result, whatever it is. This is what we call quantum entanglement. The two particles share a state. They are fundamentally intertwined. Now comes the brilliant part of the argument. Separate the two particles. Send the positron to the other side of the galaxy, billions of kilometers away. Now measure the electron with a machine called Stern-Gerlach. Let's say it collapses to spin up. At that exact instant, on the other side of the galaxy, the positron must instantly become spin down, with 100% absolute certainty, even before anyone touches or measures it. But how does the distant positron know what to do? The measurement of the electron here must have sent some kind of message, influence, signal to the positron far away, and that signal would have to travel faster than light, instantaneously, in fact, to arrive in time. There's no escaping this conclusion, not within the Copenhagen interpretation of quantum mechanics. Einstein concluded, Either there's instantaneous communication at a distance, completely violating relativity, or quantum mechanics is incomplete and there are hidden variables. Information about spin that the particles already carry from the beginning, decided when they were still together. The second option was clean, local, causal, sensible. Von Einstein bet on it. The EPR paper leaked to the press even before being officially published. Without Einstein knowing, Podolsky had given the news to the New York Times. Einstein was the most famous person in the world attacking the hottest physics of the moment. The headline read, "Einstein attacks quantum theory." The press loved it. Physicists, less so. Bohr responded with a text so obscure that decades later, experts still debate what he meant. But the community decided Bohr had won. Einstein was gradually treated as a past genius who simply couldn't accept the new. When Einstein died in 1955, the debate seemed closed. Quantum mechanics reigned. The question of non-locality had been swept under the rug. Part 6. The Man Who Remembered the Forgotten Paper. 8 years after Einstein's death, in 1963, an Irish physicist named John Bell took a sabbatical from CERN and finally decided to do what he had postponed. Think seriously about the foundations of quantum mechanics. Bell was never satisfied with the answers he received. What is a measurement? Why does the universe behave differently when observed? They treated this as unnecessary philosophy. Bell never believed that. He reread EPR, reread Bohr, and concluded, Einstein was intellectually far above Bohr on this issue. Einstein saw the problem clearly. Bohr was obscure. But Bell went further. He asked the question no one had rigorously asked. Is it possible to test which of the two options is true? Part 7. The twist Bell invented. The secret was adding a choice to the experiment. In the original EPR, the detectors were always aligned. But what if the experimenters could freely choose the detector angle independently? Bell showed that in this case, the two theories predict different results. Imagine the detectors have 3 positions, 0, 120, and 240 degrees. If both choose the same position, they always get opposite results. Both theories agree. The interesting question is when they choose different positions. Quantum mechanics makes a specific prediction about the disagreement rate, 25% of the time. And a local hidden variable theory? If the particles carry hidden instructions from the beginning, a plan decided before separation, these instructions must work for any combination of angles. When you calculate all possible strategies, you discover that none can produce a disagreement rate as low as 25%. The minimum any local theory can achieve is 33%. The difference may seem small, but it's decisive, and it can be measured. Bell published his proof in 1964, a mathematical proof that no local theory can reproduce all predictions of quantum mechanics. If the experiment showed a rate lower than 33%, locality was dead. Part 8. The experiment. It took almost 2 decades for the experiment to be done convincingly. The great test came in 1982, when French physicist Alain Aspect and his team performed sophisticated versions of Bell's experiment, using entangled photons and detectors that changed orientation during particle flight, eliminating any possibility of conspiracy. The result? Disagreement rate of 25%, exactly as quantum mechanics predicted. Local hidden variables were wrong. Local physics was wrong. Einstein was right to identify the problem, but wrong about the solution he hoped for. The universe really does allow instantaneous influences at a distance. Entangled particles really do behave as if they know each other's results, no matter the distance. Bell was shocked. Not because they contradicted quantum mechanics, he expected that, but because now there was concrete proof that the universe is non-local. As he said in one of his last lectures in 1990, "I think you're stuck with non-locality. I know of no conception of locality that works with quantum mechanics." 8 months later, Bell died unexpectedly at age 62. He had been nominated for the Nobel Prize the year before. Part 9. The paradox that survived. But if the universe is non-local, why can't we use this to send messages faster than light? When you measure your entangled particle, you get a random result. No control. Your partner, measuring theirs, also gets a random result. The results are correlated, but the correlations only become visible when both communicate through normal channels, slower than light, and compare notes. You can't control what your detector registers, therefore you can't send information. Non-locality exists, but the universe built a specific lock to prevent it from being used for communication. It's an uneasy truce between relativity and quantum mechanics. The letter of the law is respected. But the spirit, the idea that local causes produce local effects, has been violated. Einstein would have been dissatisfied, and we have reason to be too. Part 10. What if Einstein could still be right? There's one last way out. I'm an interpretation Bell didn't reject, and that has gained more defenders. The many worlds interpretation. The idea is simple and mind-blowing. When you measure a quantum particle, it's not the universe that collapses to one result. It's you who enters superposition with the particle. There are two yous after the measurement. One who saw spin up and another who saw spin down. Both are real. Both continue existing in parallel branches of the universe. If this is true, entanglement changes in nature. When the distant positron knows the electron's result, it's not because it received a message. It's because there was already a version of the experiment for each result. There's no collapse, no non-local influence, just branching of the universe. And here's the crucial point. In the many worlds interpretation, Bell's theorem doesn't apply in the traditional way. The proof assumes each measurement has a single result. But in many worlds, it doesn't. In this scenario, the universe is local. Einstein would be right deep down, even if wrong on the surface. Quantum physics and relativity aren't rivals. They're parts of the same puzzle. And perhaps the solution is stranger than either imagined. Conclusion. The legacy of the man who asked too much. What does the story of Einstein, Bohr, Bell, and entanglement teach us? That uncomfortable questions matter. Einstein was ignored, ridiculed, treated as a relic. But the questions he asked forced physics to confront its strangeness. Without EPR, Bell would have nothing to reread. Without Bell, there would be no test. Without the test, non-locality would be just philosophy. See, that science advances slowly when authority replaces argument. Bohr won the debate not because he had stronger reasons. He had more obscure reasons. But because he was Bohr. An entire generation of physicists learned not to ask the questions Einstein asked. The universe is stranger than any theory we have. Entangled particles know each other instantaneously. Measurements here affect results there. Reality perhaps branches at every instant into infinite versions of itself. Einstein didn't want such a universe, but he was the one who forced us to look at it head-on. In the end, perhaps Einstein's greatest legacy isn't relativity, nor physics' most famous equation. It's the courage to say, something is wrong here. I refuse to stop asking until I find the answer.